Hello class. In this video we'll learn how chemists determine the formulas of substances. So we will start from percent composition. We already learned about percent composition. You know what it is. It is the percentage that each element contributes to the total mass of the substance. We took the example of water, in which case hydrogen represents about 11% by mass, and oxygen represents 89% by mass. And the way we got that, if you guys remember, we said that hydrogen has a atomic mass, or a molar mass if you want, of 1 gram per mole. So 2 hydrogens, that's 2. And the total molar mass of water is 18, so 2 over 18 is about 11%. And likewise, we have only 1 oxygen, so 16 over 18 is about 89%. So this is how we do percent compositions. Now we are going to be using this knowledge of a percent composition and determine the formula. So in this slide, what we did is we went from the formula of water, which is H2O, and then from that we determined the percent composition of water, which is 11% by mass hydrogen and 89% by mass oxygen. What we are going to be doing in the following slides is actually the exact reverse. We'll go backwards. In other words, we will go from the percent compositions to the formulas. Okay, so we can go from formula to percent composition, and we can also do the reverse. Before we start doing that, here is a learning check in which you can actually practice determining percent compositions. So you can do this too, and then the rest of them we will do in class. All right, I hope you enjoyed doing those couple of percent composition questions. So as we said, percent compositions can be used to determine the formulas of compounds, and we will learn how that is done. Well, let's take the example that we already did before, which was the example of water. So we went from the formula H2O to the percent composition, which is 11% again by mass hydrogen and 89% by mass oxygen. So let's see if we can go from these two percentages to the formula of water, which is H2O. There are a few steps to follow. The first step is pretty simple. We just replace the percentage sign by gram. So we go from percentages to masses. So 11 grams instead of 11% hydrogen, and 89 grams oxygen instead of 89% oxygen. So that's easy enough. Step 2, we get the number of moles. If you guys remember a few slides ago or a few videos ago, we learned that the number of moles is equal to my mass divided by molar mass. In other words, mass equals number of moles times molar mass. So if you solve for a number of moles, you get mass over molar mass. Now, do you know the mass of hydrogen in this sample? Yes, it's 11 grams. How about the mass of oxygen? That's correct, 89 grams. Now all we do is divide those masses by the molar mass of each one of those two elements, namely 1 gram per mole for hydrogen and 16 grams per mole for oxygen. There we go. So we get 11 moles of hydrogen and 5.6 moles of oxygen. Step 3. We need to get the mole ratios, and we do that by dividing the larger number of moles by the smaller one. In this case, hydrogen has a higher number of moles because it's 11, remember from the last slide, and oxygen was 5.6. So we go 11 divided by 5.6, and we get about 2. Now, I'm sure you guys see where we're going with this. Now, since the ratio of hydrogen to oxygen is 2, therefore, that for every 2 hydrogens, there is 1 oxygen atom. And ta-da, we have the formula of water, which is H2O. Now, please note that it is better not to be rounding the masses from the periodic table too much. So be careful, and it's preferable not to round at all, unless it's really close to a whole number, such as the case of hydrogen or oxygen. Oxygen is, I believe, 15.999. So that's really close to 16. So in that case, you can pretty much always round. Hydrogen is also pretty much 1 because it's 1.00 I don't know, 7, 8 or something. So those cases are very close, so you can round. But the other elements, be careful not to round. But we'll talk more about this in class. Well, here is another example. Let's say a chemist found a substance and then sent it to an analysis lab, and the analysis lab sent back the results, and the results say that this substance, whatever it is 36.84% nitrogen and 63.16% oxygen. Now, there are some labs that do this kind of analysis, okay? Now, once you get this data, you should be able to go ahead and figure out the empirical formula. Let's go ahead and just apply the rules that we learned in the previous slide. So we change the percentages into masses. Therefore, these are the masses of nitrogen and oxygen in that sample. In a sample of 100 grams, I should say. And then we should get the number of moles by dividing each mass by the molar mass of the corresponding element. So we get this for nitrogen and this for oxygen. Now, do you remember the next step? That's correct. We divide the larger of the two numbers by the smaller one. So we go O over N is 3.95 over 2.63, and we get 1.5. Now, what does this mean? What this means is for every oxygen we have, for every nitrogen we have 1.5 oxygens. So N1, O, 1.5. But we never write formulas, with the decimals. So we go ahead and multiply. In this case, we multiply everything by 2, and we get N2O3. There you go, and that's the formula. See how easy that is? This is how we get empirical formulas from percent compositions. Go ahead and try and see if you can figure out the formula of the substance that is 56% vanadium and 44% oxygen. Give it a try, and let's see how that goes tomorrow in class. All right, I hope you enjoyed determining the formula of that substance, and maybe you looked at the PowerPoint and maybe you did more of that, and that's fantastic. So now we move on to molecular formulas. Once you understand empirical formulas, molecular formulas are pretty straightforward. We should know that several substances can have the same empirical formula, such as these three. What is the empirical formula of these three? Think about it. Very good. You simplify and you get CH. Now, if you calculate the percent composition for each one of these substances, you find the same thing, which means that just getting the empirical formula is not enough, because the empirical formula could be for several different molecules. So we need something better than the empirical formula to identify the molecules or the substances. Okay, so empirical formulas do not always identify substances. Okay, let me repeat again. Empirical formulas do not always identify molecules. For example, the two molecules we are looking at right now, benzene and C2H2, these have the same empirical formula, which is CH. So again, we need better than the empirical formula. Now, that thing that's better than the empirical formula is called the molecular formula. In order to determine the molecular formula of a compound, we must be given the molar mass of the compound. Okay, and then we compare it to the molar mass we get from the empirical formula. Now, luckily, there are labs or there are chemical methods that you can use to determine the molecular molar mass of a substance. So again, if let's say again you were a chemist and you find a substance, you can send it to two different labs or to the same lab. They can return to you the percent composition and the molar mass, and from those two things you could determine the molecular formula. How? This is how the molecular formula is always an integer times the empirical formula. So the molar mass from the molecular formula is always n times the molar mass from the empirical formula, and n is an integer. For example, benzene will have a molar mass that is 6 times the molar mass from the empirical formula, which was CH. I hope this makes sense. And here's a second example. And let's practice this and see how it goes. Do you think you could figure this one out? go for it. See if you can do it, and we will be doing it and a few more examples in class. All right, I hope you enjoyed this, and this is the end of this video. See you in class. Thank you.